Now that we're familiar with the idea of gradient descent, it's time to just mention a couple of variations on the gradient descent algorithm. There are many different ways to perform gradient descent, and there are many different methods and tactics. It's not really feasible for us to discuss all of them, but two variations on gradient descent that really what they aim to do is either reduce the amount of data that we have to use or to somehow optimize and make the process a little bit better. So remember, the idea here is just always that we're taking some parameter set. We've called it theta before, but it doesn't matter what you call them. To get the next value of your parameter set, which in some cases could be like a slope and an intercept. Perhaps that's what we're dealing with. And to get the next slope and intercept, we take the previous slope and intercept, we apply some sort of learning rate to it, which for us, this has been mainly constant, and we take that learning rate times the gradient of the function at the current point. And so what this has us do is if we have, a space and we're playing with the slope and the intercept, and this probably is a three-dimensional problem, then coming towards us we have like a z-axis that is perhaps the sum of squared residuals. And so maybe what we're doing is we start off with an initial value and we kind of, move around and eventually find our way to the minimum as we iterate this over and over again. Now, one of the problems that we can have is that as this bouncing around occurs, maybe it's excessive because our learning rate is, it's fixed, and as a result, maybe if the rates are really large, it causes us to overshoot our minimum for quite a while. And so if we think about this as similar to maybe a heavy ball, let's say in sort of a two-dimensional perspective, I put a heavy ball right here and release the ball that ball has a momentum to go downhill. And gravity is, of course, forcing this thing. And so what's going to happen is this ball is going to have a lot of momentum. It's going to roll faster, right? And as it gets here, it's going to slow down, but not fast enough. And it's probably going to overshoot and then come back and roll the other way and roll the other way. And then eventually it'll settle down in that gully. Well, to facilitate in slowing that down, we can incorporate what we call momentum. And if you notice how this is going to be phrased, it's exactly the same way. There's our standard gradient descent. Standard gradient descent. But what we'll do is we'll add one more term, and we're going to call this the momentum term. So right here we have the momentum. And essentially what it's going to do is it's just going to add in an extra little piece that will weigh against our step size. So we still think about this as a momentum kind of extra step size. And it will get weighted by a factor of alpha. So alpha will just be some number between 0 and 1. And this is just a weight. And literally what we mean by a weight is it's going to have some bearing on the next value of our parameters that we get upon this iteration. And so we're not going to talk about how to choose that, but of course, the closer that is to 0, the lesser of an impact this momentum term will have. The closer it is to 1, the more impact it will have. And then you have this delta xk in here, and delta xk is really just a memory. It's a memory of what happened previously. And so what delta xk will represent is it will represent the difference between our current parameter set and our previous parameter set. So maybe it looked like this. Let's say we had 2, 4 was our x vector, and we'll say that this was x0. That was our initial choice, and then maybe we went to 3, 6, and then maybe we went to -1, 4. And so these were our x0, x1, and x2. So to get x2, for instance, what we're going to do is we're going to take our x1, subtract away our step size, let's say it's our learning rate, let's say it's 0.01, and whatever our gradient is, maybe our gradient is 0.43 or something like that. And so now maybe we choose an alpha to be a half. Maybe that's our choice of the alpha. And now our delta x sub k will be the difference between our current x, which is 3, 6, minus the previous one, which was 2, 4. So to get this x2 right here, notice that it doesn't only depend on the gradient corresponding to x1, but it also depends upon how much change occurred between x0 and x1. So it has a little bit of a memory, and so we're going to weigh that into the equation. And so if this was a really large change, then it will carry some weight in our current change. If it was a really small one, then again, we want it to carry some weight in our current change. So that is pretty much working with momentum. And so we're not going to actually iterate through this process because, as you can see, it just requires this extra computation, which we can set up through a coding language. Now, another important one, and so, by the way, gradient descent with momentum sort of helps the convergence process take place a little bit faster by incorporating what happened previously. Now, stochastic gradient descent, what it aims to do is to, when we're working with big data, think big data here. And big data just means we have a lot of data, right? A lot of it. And so when we have a lot of data, gradient descent can become very computationally expensive. Let's imagine that we have 10 million samples on 3,000 variables. Okay, so what we have basically is we have 10 million ordered 3,000 tuples, right? So basically this means maybe we have person 1, and maybe we collect a bunch of data on them, all kinds of medical data and gene data, and we have all the way up to person 1 million. And so what we're going to collect on person 1 is we're going to collect maybe what we'll call P11. So that's going to be person 1, and then the first data value, person 1, second data value, and we have 3,000 variables. So we're going to take 3,000 measurements on that one individual. So I'll just write 1, 3,000. And so that will have 3,000 components. And also on this 1 millionth person, we'll again have 3,000 components. So if you do the math on this and you're like, well, if each of these variables requires a derivative, then you'll have the partial of your function with respect to variable 1 all the way up to the partial of your function with respect to variable 3,000. And that's a lot of derivatives. But now keeping in mind, you have to calculate that for the 10 million, sorry, this should be 10 million, not 1 million, to the 10 million individuals. So that's going to require, if it's 3,000 derivatives per person, then you're going to need 3,000 times 10 million, which is 30 billion. Total derivatives will need to be computed per one iteration. And that's key here. This is just one iteration of this algorithm. But since we usually run at least 1,000 iterations, that is 30 trillion computations for gradient descent. So gradient descent is very inefficient for large data. You can see that's going to take a long time for a computer to do. So wouldn't it be nice if we could figure out how to compute fewer derivatives? Well, stochastic, this really, I want you to think of stochastic as involving randomness. And stochastic gradient descent will actually incorporate randomness. So rather than taking the 10 million samples, so let's imagine, here we have all of our 10 million samples. And instead of selecting all of them at each iteration, let's take a mini batch. And a mini batch means that we're going to take not 10 million, but we'll take m of those 10 million. Now that mini batch size may be that we only look at one of the samples at each iteration. So literally we would compute our change in parameters based on just that one 3,000 variable vector. Or we could, obviously make that mini batch all the way up to the total size, in which case that's just standard gradient descent. It's no longer stochastic, right? Because then you're taking everything. It's what we call deterministic. And so perhaps what you do is maybe you just take a mini batch of maybe 3 samples, and you only use those 3 samples to update your say slope and intercept. And so based on those 3 samples, you get a new one. And then the next time, the next iteration, you take, again, from those 10 million, you just select 3 samples at random. And you can have a computer do this for you. It'll just select randomly 3 samples. And notice by what factor that decreases the amount of computations. Instead of having 10 million samples times 3,000, if it were 3 samples times 3,000, well, that's only 9,000 computations per iteration. And now if you multiply that by 1,000 iterations, that's only 9 million computations as opposed to 30 trillion. So much, much different, or 30 trillion, sorry, down here. Much, much smaller. And so 3 is just a one size. We're not declaring what should be the best mini batch size. Obviously, the bigger the better. You're going to get more precision, so there is a trade-off, but it can be shown that under enough iterations, this method converges to the same value that we would get under standard gradient descent. Now, these are just 2 methods to kind of illustrate variations on gradient descent, so that you can see that there's lots of research and lots of literature out there on different methods under different circumstances, and it just really depends on what you're doing with gradient descent.